Hello dear students, welcome to this video lecture on Applied Mathematics, Session 11. In this video we shall discuss inverse Laplace transforms, that is, inverse Laplace transforms of integrals. You recall the property of Laplace transforms that you have discussed in your previous video lectures, that is, if L of f of t is equal to f of s, then Laplace transform of f of t divided by t is equal to integral s to infinity f of s ds. It is one of the important property of Laplace transforms that you have discussed in your previous video lectures. Inverse Laplace transforms of integrals. Let us see this in the form of a theorem. The statement of the theorem is like this: if L inverse of f of s is equal to some f of t, then L inverse of integral s to infinity f of s ds is equal to f of t by t. In order to prove this result, first we have to prove the result L of f of t by t is equal to integral s to infinity f of s ds. That is one of the important property of Laplace transforms. The proof goes like this. We know that from the properties of Laplace transforms, if L of f of t is equal to f of s, then L of f of t by t is equal to integral s to infinity f of s ds. In order to prove this result, we need to first prove this one. Then only we can prove this result. Applying L inverse on either side of the equation 1, we get L inverse L f of t by t is equal to L inverse of integral s to infinity f of s ds. So therefore, which proves the required result, that is L inverse of integral s to infinity f of s ds is equal to, here L and L inverse operators to each other, therefore they gets cancelled. We get f of t by t, which is the required result of the given theorem, that is L inverse of integral s to infinity f of s ds is equal to f of t by t. Now let us see some of the problems on that theorem. First one, find L inverse of 1 by s plus 1 whole square using Laplace transforms of integrals. Of course, there are many methods to find. We are having many methods for finding L inverse of this function, but here we have to use Laplace transform of integrals method to find the L inverse of this function 1 by s plus 1 whole square. The method or solution goes like this. You take this L inverse of 1 by s plus 1 whole square as some function of t, and further you take 1 by s plus 1 whole square, this function, as capital F of s. Now integrate this with respect to s from s to infinity. We get integral from s to infinity f of s ds is equal to integral from s to infinity 1 by s plus 1 whole square ds. Now we know that integral of 1 by x square is minus 1 by x. I am using that result. So therefore integral of 1 by s plus 1 whole square is minus 1 by s plus 1, and between the limits s to infinity. After applying the limits of integration, the upper limit is s tends to infinity, so we get 1 by infinity here we are having. So 1 by infinity is 0. So therefore when we apply the upper limit, the value of this is equal to 0, and minus lower limit you put s is equal to s, so we get 0 minus s plus 1, 0 minus 1 by s plus 1. Because of this minus, the answer turns out to be 1 by s plus 1. Now L inverse, taking or applying L inverse on either side of the above result, we get L inverse of integral s to infinity f of s ds is equal to L inverse of 1 by s plus 1. but we have proved this result L inverse of integral s to infinity f of s ds in the form of theorem to be equal to f of t by t, and it is the standard result. N inverse of 1 by s plus 1 is e power minus t. Okay, so therefore finally we get f of t by t is equal to e power minus t. On cross multiplying, t comes here, therefore f of t is equal to t into e power minus t, but we have taken this f of t to be equal to L inverse of 1 by s plus 1 whole square, the given problem, that is equal to t into e power minus t. This is what is the answer for the first problem. We shall move on to the second problem now. Second problem, find L inverse of 2s by s square minus 4 whole square using Laplace transforms of integrals. The method of solving this problem is same as that of the first problem. So you take L inverse of this function as some f of t and 2s by s square minus 4 whole square as capital F of s. Now you integrate both the sides with respect to s between s to infinity. So we get this. So integral s to infinity 2s by s square minus 4 whole square ds. Now how to integrate this function 2s by s square minus 4 whole square? You see, if I differentiate denominator s square minus 4, you will get derivative of s square is 2s. So therefore we get the numerator. So in that case we can go for substitution method. So what I do is I am going to substitute s square minus 4 is equal to some t or some y. On differentiating that you will get 2s ds is equal to dt. Therefore in place of 2s ds we can write dt, and in place of s square minus 4 we can write t power 2. So the integrand now becomes dt by t square, whose integration is equal to minus 1 by t. So the answer is minus 1 divided by t is nothing but your s square minus 4 between the limits s to infinity. So after applying the limits of integration as in the previous case, we are going to get this result 1 by s square minus 4. Now you take L inverse on either side. So we get L inverse of integral s to infinity f of s ds is equal to L inverse of 1 by s square minus 4. And as you know, this is f of t by t and this is the standard result. So therefore the answer is f of t by t is equal to, it is sine hyperbolic 2t. On cross multiplying we get this. Now you take this f of t as the given problem, L inverse of 2s by s square minus 4 whole square, that is equal to t into sine hyperbolic 2t. That is the answer of the second problem. Third question, find L inverse of h plus 2 divided by s square plus 4s plus 5 whole square using Laplace transform of integrals. First you take L inverse of this function as some function of t and take f of s is equal to s plus 2 divided by s square plus 4s plus 5 whole square. You integrate on either side with respect to s between s to infinity, you will get this. Now if I integrate this one by substitution method, we can integrate this one, because if I differentiate denominator we get s square plus 4s plus 5. The derivative of this is 2s plus 4 we get, but in the numerator we have only s plus 2. So for that you multiply and divide by 2. So here in the numerator, in that case I get 2s plus 4, which is the derivative of the denominator. So we can put s square plus 4s plus 5 is equal to t and differentiate that, you will get 2s plus 4 ds is equal to dt. So therefore in the numerator we are having 2s plus 4. After multiplying and dividing by 2, 2s plus 4 into ds, we can replace it by dt divided by this quantity is t power 2. So it becomes dt by t square, whose integration is minus 1 by t. So therefore the answer is minus 1 by s square plus 4s plus 5. So and where it comes, this 2. So this comes after multiplying dividing by 2. So therefore we get minus 1 by 2 times 1 by s square plus 4s plus 5 between s to infinity, and after applying the limits of integration you will get this 1 by 2 into 1 by s square plus 4s plus 5. Next you take L inverse on either side. L inverse of integral s to infinity f of s ds is equal to 1 by 2 constant, take it outside, L inverse of 1 by s square plus 4s plus 5, and this LHS function is nothing but f of t by t. In RHS we are having L inverse of 1 by s square plus 4s plus 5. In order to find the inverse Laplace transform of this function, you write this 5 as 4 plus 1, so that s square plus 4s plus 4 can be written as s plus 2 whole square and plus 1. So by applying the shifting property we can easily find out or evaluate L inverse of this one. So therefore we are having finally f of t by t is equal to 1 by 2 L inverse of, this is s plus 2 whole square, the 5 can be split as 4 plus 1, so that s square plus 4s plus 4 is s plus 2 whole square and remaining plus 1. So by applying the shifting property we get 1 by 2 times e power minus 2t, this is e power minus 2t into L inverse of 1 by s square plus 1, which is the standard result. So therefore we are having f of t by t is equal to 1 by 2 e power minus 2t into sin t, and cross multiplying we will get this one, but f of t is the given problem, L inverse of s plus 2 divided by s square plus 4s plus 5 whole square is equal to 1 by 2 t e power minus 2t into sin t, which is the answer for the given problem. Next and the last problem, prove that L inverse of integral s to infinity 1 by s into s plus 1 ds is equal to 1 minus e power minus t by t. The proof or solution goes like this. You take this function 1 by s into s plus 1 as 1 f of s. So now 1 by s into s plus 1 can be resolved like this, 1 by s minus 1 by s plus 1 using partial fraction technique. Now you take L inverse on either side. So L inverse of 1 by s and L inverse of 1 by s plus 1, they are the standard results. Therefore L inverse of 1 by s is 1 minus L inverse of 1 by s plus 1 is e power minus t. I call this result as f of t, and therefore L inverse of integral s to infinity f of s ds, we know this result, we have derived this already, that is f of t by t. Therefore L inverse of integral s to infinity f of s is 1 by s into s plus 1 ds is equal to this f of t, we have taken it as 1 minus e power minus t divided by this t, which proves the required result. These are all the problems that comes under inverse Laplace transforms of integrals. Hence proved the result. Thank you.